In this video, we talk about real gases. A gas that obeys the ideal gas equation as well as the gas laws under all conditions is said to be an ideal gas, or a gas that behaves ideally. In reality, all gases deviate from ideal behavior to some extent and are described as real gases. With real gases, some of the assumptions made about ideal gases no longer apply under these certain conditions. And these are the two conditions. The first one is high temperature. So at a very high temperature, the gas particles are closer together. Under these conditions, the actual volume of the particle is significant. So when you increase the pressure, the volume goes down, so the volume becomes significant. The second condition is low temperatures. So at low temperatures, the particles move less rapidly or have lower average kinetic energy. This means that there's greater opportunity for intermolecular forces between the particles to have an effect. So all that I'll be explaining in this video is related to these two conditions. And also you should know that these are the two conditions under which gases can be liquefied, which also suggests that under these two conditions, the force of attraction between the particles is very high. Next, we have a graph showing deviation at high pressures and low temperatures. So this graph was plotted for nitrogen, where we have PV over RT on the y-axis and pressure on the x-axis. PV over RT is the same as mole from the ideal gas equation. This is the equation I'm talking about. PV is equals to nRT. So using the conditions of temperature and pressure at STP, standard temperature and pressure, the product of PV over RT for an ideal gas is always equal to 1. So to demonstrate this, let me do a calculation where n is equal to 1.00 times 10 to the power 5. That's the STP for pressure times 0.0227 meter cube. That's the volume for standard for STP, and R is the universal gas constant at 3.14 times 273 Kelvin. That's the temperature. So after calculating this, you'll get 1. So this one is for the ideal gas, as you can see here. So at this 1 mole or PV over RT, this is the most ideal gas. To interpret this graph, we have 3 different temperatures: 200K, 500K, and 1000K. So the temperature that has shown the biggest or the largest deviation from the ideal gas of 1 is this one with the smallest temperature, which is 200K. So this shows us as at low temperatures and high pressure, real gases cease to be an ideal gas. The reason for this is at high pressure, the molecules or atoms come sufficiently close together for intermolecular forces to operate. The particles are attracted to each other, and at low temperatures, deviation from ideal behavior increases because the molecules are moving more slowly or the kinetic energy is slower. So this allows the intermolecular forces between neighboring molecules or atoms to become significant. So some gases are more ideal than others. So we have hydrogen, nitrogen, methane, helium, carbon dioxide, and the ideal gas. So the degree of deviation from ideal behavior varies from the degree of deviation from ideal behavior varies for different gases. Gases that show the most ideal behavior are those with a low molar mass and the weakest intermolecular forces between the particles. That's why you see helium is closer to the ideal gas because it has a molar mass of 2, but gases such as carbon dioxide, methane will deviate the most from the ideal behavior. This is because there is a strong intermolecular forces between the molecules, or even worse for ammonia, which has a hydrogen bond, which is the strongest intermolecular force of attraction, the deviation from ideal behavior is even greater.